November 7, 1940. A suspension bridge over Puget Sound is twisting, not swaying. Twisting. One sidewalk rises while the other drops, and the roadway between them tilts like a ribbon being wrung out. A man crawls along the center line because he cannot stand up on it. His dog is still in the car. The wind that morning is not a hurricane. It is the kind of wind that makes you zip your jacket. And the bridge has only been open to traffic for 4 months. Nobody watching yet understands what they are looking at. By the end of this file, you will know exactly why that deck twisted, and you will be able to explain it to someone else in about 2 sentences. Not with the phrase resonance, which gets used as a spell rather than an explanation. With the actual chain, what the wind did, what the shape of the bridge did with it, and which decision made years earlier on paper made the collapse possible. You will also know which part engineers are still arguing about because there is one, and it matters. Start with what almost everyone believes happened. The folk version goes like this. Freak wind. A gust from an unlucky direction, hitting the bridge at the one frequency it could not handle, like a singer shattering a glass. Wrong place, wrong moment, 1 in a million. It is a reasonable story. It matches the footage, where the wind seems to be doing all the work, and it lets everyone off. Nobody made a mistake. The sky did. That version survives because the alternative is harder to look at. The record does not support it, so go to the record, start with the money and the shape, because they are the same story. The Tacoma Narrows crossing was planned during the Depression, and the cheaper the bridge, the likelier it got built. Leon Moiseff, the bridge's lead designer and a consultant on the project, produced a slender design. Washington State's Transportation Department credits him as the designer who redesigned the crossing to a lighter form. Clark Eldridge, the state's engineer, supervised construction. The deck ended up 39 feet wide with stiffening girders 8 feet deep. 2 lanes and narrow walkways. For a main span of 2,800 feet, that is extraordinarily thin, and thinness is the first pin on the board. Compare it to what came before. The George Washington Bridge and the Golden Gate carried far deeper stiffening trusses. Deep open trusses do 2 things. They resist bending, and they let wind pass through them. Tacoma Narrows had neither. Its solid plate girders were shallow, and instead of letting air through, they blocked it, so the deck behaved less like a bridge and more like a wing section held sideways in a river of air. That was not a secret discovered afterward. Something was noticeably wrong from the day it opened, July 1st, 1940. The bridge opens. Almost immediately it starts moving up and down in the wind, enough that drivers noticed cars ahead of them disappearing into a trough and rising back into view. Locals gave it a name, Galloping Gertie. People drove across it for fun. Some found the motion made them ill. Tolls were doing well. And here is the part that makes this a case file rather than an accident. The motion was known, reported, and being actively studied. Somebody was already trying to fix it. Engineers tried damping the movement. Hydraulic buffers were installed at the towers. Tie-down cables were anchored from the deck to the ground on the shore side. The cables snapped. Steel cables were run from the girders to the main cables to try to hold the deck. The bridge kept galloping. Every fix treated the vertical bouncing as the problem, because the vertical bouncing was what everyone could see. Meanwhile, the University of Washington was running wind tunnel tests on scale models to work out what was driving it. Frederick Burt Farquharson led that work. His first studies concluded on November 2nd, 1940. 5 days. That is the gap between the first studies concluding and the deck coming down. Now the morning itself. November 7th, 1940. Wind through the Narrows, and the deck starts its usual vertical galloping. Recorded wind speeds that day are generally given at around 40 miles per hour, with sources varying a little on the exact figure. The bridge had been designed with much stronger winds in mind, in the range of 100 to 120 miles per hour, so this was not a storm the structure was unprepared for on paper. Then the motion changed character completely. Around mid-morning, a cable band at mid-span slipped. The deck stopped bouncing evenly and began twisting instead. One edge up, the other edge down. The whole roadway rotating about its own center line. Traffic was stopped. Leonard Coatsworth, a Tacoma News Tribune editor, was on the bridge and had to abandon his car and crawl to safety, leaving his daughter's dog behind. The dog did not survive. The twisting kept building, not fading. The tilt reached angles that make the surviving film look like a special effect. That distinction, bouncing versus twisting, is the whole case. At around 11 in the morning, a section of the center span tore loose and dropped into Puget Sound. More followed. When it finished, the middle 600 feet of roadway was gone, and the towers were bent inward. Nobody was killed. The film exists because Barney Elliott of a local camera shop was there shooting it, which is why this failure, out of all the failures of that era, became the one every engineering student watches. Which leaves the question the footage cannot answer on its own. Why did the twisting grow instead of settling down? Here is the mechanism. When steady wind hits a blunt, solid deck, it does not flow smoothly past. It separates and rolls off the edges as vortices, alternating top and bottom. Each vortex shed off an edge gives the deck a small push. If those pushes happen to arrive in step with the way the deck naturally wants to twist, each one adds a little more energy than the structure can shed. And, crucially, once the deck starts moving, the motion itself changes how the air separates. The bridge became a participant in the force that was destroying it. That is the feedback loop. Wind pushes the deck twists. Twisting presents a new angle to the wind, which increases the push. More push, more twist. Nothing is fighting back hard enough to stop it, because the deck is too shallow and too flexible in torsion to resist rotation, and there is no open truss to bleed energy out. Energy goes in faster than the structure can absorb it. The amplitude grows every cycle until steel gives way. Not a freak gust, a moderate wind, applied patiently to a shape that let it in. So the design was tested for wind pressure, static pressure, a wind blowing hard against a solid thing. The bridge passed that test comfortably. What was not tested in the design stage was what a moving, twisting deck would do to the air around it, and what the air would do back. The failure was not that the wind was stronger than expected. The failure was that the question asked was the wrong question. That is why this collapse ended up in every textbook. Now, why does something like this feel like bad luck? Because the bridge stood for 4 months. Every single day it did not collapse looked like evidence that the galloping was a quirk, an odd feature of a new bridge, something to get used to. 4 months of successful crossings against one bad morning. Human memory weights it the wrong way. If you find this sort of thing worth digging into, subscribing genuinely helps, because these case files take a while to check. The other reason it feels like luck is timing. The studies were underway. The fix was being worked on, which makes it look like a race lost by days. It was not. The twisting mode that destroyed the deck was already available to it from the day the last rivet went in. The wind that could trigger it blows through the Narrows regularly. The only variable left was which morning the cable band slipped and the motion changed shape. Given enough mornings, one of them was going to. That is the uncomfortable part. The collapse was not scheduled, but it was permitted. There is still something the record does not settle. Engineers still argue about the precise label. Simple resonance, where wind pulses happen to match a natural frequency, is the version taught in a lot of physics classes. Many specialists say that is too neat, and that the correct description involves aeroelastic flutter, where the deck's own motion generates the destabilizing forces. The two overlap, and the terminology gets contested. Reported wind speed that morning varies slightly between accounts. Exact timings of the collapse sequence differ depending on which report you read. And responsibility was argued over for years afterward, publicly and bitterly, in ways the record does not tidily resolve. What is not disputed is what changed afterward. Wind tunnel testing of scale models became standard practice for long-span bridges. Decks got deeper, stiffer in torsion, and open enough to let air through. The replacement bridge that opened in 1950 used a deep, open, stiffening truss and grated openings in the deck. The lesson was not be afraid of wind. The lesson was that you have to test the thing you did not think to test. That is the entire discipline in one sentence. Murphy's Law gets quoted as a shrug. It was never a shrug. It was a design instruction. If a part can be assembled the wrong way, someone will assemble it the wrong way, so build it so it cannot be. Tacoma Narrows is the same instruction written in steel. If a deck can be pushed into a twist it cannot escape, one ordinary Thursday will push it. The wind did not choose that bridge. The bridge left the door open. Next file, a machine that worked perfectly and destroyed itself doing exactly what it was told.